this week lecture or seminar or telecast, you want you. This week we are going to continue our spatial data science, and I will say you are welcome to this other session of this spatial data science, where we'll be considering majorly spatial data, how we can analyze them, how we can get information from them. And in the previous lecture, let me call that one session one of this course. I labor on the basic principle of Python, how to use Python, the key elemental elements of Python, like function, creating method, defining method, importing your function. So now we are going to apply what we learned in the first session in this advanced session. So I welcome you once again. And this session is going to be interesting because we will be playing with data that we are used to as a geomaticians, and then we will be making sense out of those data. So you are welcome once again. So today, to start this session, we'll be starting with mapping in Python. We look at all the packages that are available for us to map, to present our map, to manipulate spatial data in Python. So this lecture, the main aim is to learn how to load spatial data, how to manipulate spatial data, and how to visualize spatial data. In some sense, spatial data are usually included simply as one or more column in a table. When we look at our shapefile, we discover that they are more or less like a table. And the spatial data will now be included in one of the columns. That's how shapefile work at the background. So that is what we are going to be seeing also in this course. However, spatial is special. So spatial is special. Let's mark that very well. It's not like any other data, just like the one I handled last week. There's no any spatial data included in it. So, but spatial is special in the sense that the way we manipulate non-spatial data is not the same way we manipulate spatial data. Spatial data, it can even include non-spatial data, and all joined together, you can analyze them together. So spatial is special sometimes, and there are few aspects in which geographic data differ from standard numerical tables. So in this session, we will extend the skill developed in the previous ones, in our previous classes about non-spatial data, and combine them. In the process, we will discover that although with some particularities, dealing with spatial data in Python largely resemble dealing with non-spatial data. So let's note this. For this class, I will like to import all these classes. By now, this should not be strange to us. Now, the first thing I will be importing here is the Matplotlib inline. This helps me to plot my map in this notebook. I will be sharing this notebook at the end of the class, please. This command helps me to plot my map in this notebook. That's what this command is doing. Again, you will see I'm importing Geopandas. If you remember or you can connect in our previous class, I use pandas. I will just say import pandas. For now, it's Geopandas. It's a package, it's a Python package that we need. And it's an extension of pandas package, extension of pandas package to handle geospatial data. So let's note that. There's this another package called OSMNS, is used to actually pull data from the internet. So we'll be using it. Also contextually, is this one help us to add base map to our drawing at the background. So also this Kepler help us to have an interactive map. So we'll be using it. And also just plot lab, as I have import it right from the first line. So this is what I will be using. For those who have been asking, can I use this thing on my local machine? If I don't want to be, if I don't have internet and I want to use it on my local machine, yes, I have a good news. Like what I'm using today, I'm using it on my local machine. So I will be sending a link on how to install all this package already installed for you and containerize in what we call Docker container. You can read more about that. We have to know all this technology because the way things is changing is beyond. If you are in this thing before, maybe 2 years ago, you may be lost if you are not following what the technology is actually doing. So now there's what we call container. Inside that container, all what you need is here. Your own is just to install it and pull out with just a simple command, and you will have your Jupyter notebook. So I will be sharing a link. If you are on Mac, if you are on Windows, just follow based on your operating system, or if you have a Linux system, just follow the procedure and you will have it installed on your local machine. So like now, I'm using it on my local machine. As you can see, I have a lot of logout. As I'm interacting, it's logging out a lot of things. So that's taken. If that is taken, let me just run this to import all these code. And as you can see, it's indicating star, means it's running, it's importing those packages. And you see, he has given me a line number to tell me that he has finished installing those, calling those packages that we need for this course. So let me quickly talk about the data set I will be using in Geospatial and feed. We have different type of data. Today, we will not depart from that. We'll be using polygon data, which is a cities data. It's a cities data used by Reproject 2019. In one of his paper, he proposed a machine learning algorithm to delineate city boundary from building footprints. These are wonderful projects that we also can do maybe at the end of the course, where we use machine learning. When we have building footprints, then we can call out what the boundary of that place is based on the building footprint. Maybe an estate, if you don't have the boundary of that estate, you can use machine learning to actually pull out what the boundary of such an estate is. So we'll be using data from that research, and to get that data in, we just to go to this URL. So let's see the nature of this data. Let me open a new tab. So you see, it's just downloading for me, but let's not worry because let me see. It's GeoJSON data, but it has been grabbed together. So, but to use it, okay, you see, it's open from Multilayer. Let me continue. I will come back to this later. So, I want to import the data, and the way to read the data directly is using Geopandas, which I have imported earlier. Then read file. then I will put the URL of that file there. So, and it will read it. So let me run this. See, it's running. As it, anytime it shows star like this, it's running. You have to wait for it. It's pulling that data. It's pulling that data. So at the end, after pulling, it will give it a line number to tell me that it has pulled it. Yes, it has done. It's done. So if you look at it at the background, it will tell you also what is going on. So now, and the second data set we'll be using also is a street. A street. And this data set from the project called Lisde Basti Majra. So it's a community-derived being initiative exploring the extent to which streets are named after women. So we'll be pulling out this data set, which is in GeoJSON format. So to tell you that we can read GeoJSON format directly without any problem. So is all these data are coiled out from Spanish city in Zaragoza. So not worry, very soon we start using the data from Nigeria or places closer to us. So that's it. And to read this data, I create a variable called URL and I put the URL in a tuple here and I just run it. Let me run it. So it should give me this URL. So if you go to this URL, you will see that we have a JSON. You see, these are the street data in JSON format. So let me close this. So I have to read it in using Geopandas again. Read file, and I put in the URL. So as simple as that. Enter. So it's running. As you can see, he indicates the status with star, showing that it's running. It's running now. So when it's finished running, it gives it a line number. So let's wait for it. But before it's done, let me talk about the last data points, the data that we'll be using, which is points data. The one I'm loading presently now is line data, which is the street. Don't forget, I attach what I read out of these Geopandas. I attach it to a variable called street. So please note that. Now, the last data set, which is point data, is we want to grab bars, that is bars that we have in Spanish, places where they sell drinks, hot drinks like alcoholic drinks in Spanish. So we want to use it. Let's see what we get out of it. So to get this, we grab it from OpenStreetMap. We all know OpenStreetMap. So, and we will grab it by querying the OpenStreetMap. So Python has a very powerful command to query OpenStreetMap using this library that we imported, OpenStreetMap-S. So, and the command we are going to be using to query this OpenStreetMap is POI from place. That's the command. So we will call the package osms.poi from places. So, and the places where we want is Zaragoza, Spanish. If it is to be in Lagos, you just put Lagos, Nigeria. So that's just it. And you will not tag. My tag will not be amenities. And the amenities is bar. So we can read more about OpenStreetMap, how they classify their data so that we can query out of it. So I want to run this and I will attach it to a variable called POIs. So let's see. So it's pulling that data. So and it's done so fast. So you do not need to know at this point what happened behind the scene where we run POI from places. But if you are curious, we are making a query to OpenStreetMap, almost as if you type bar in Zaragoza, Spain, using Google Map, and it will bring out all the bars that we have. Now, getting the response as a table of data instead as a website with interactive map. So we have been able to pull out those data. So let's inspect them. So inspecting the what? Spatial data that we have pulled out. We will start by saying the most direct way to get from a file to a quick visualization of a data is by loading it as a geodata frame. Don't forget, in our previous course, I talked about DataFrame, that pandas use DataFrame. But now we are using Geopandas. So it's now GeoDataFrame. Now, I'm calling the plot command. The main library employed for all of this is Geopandas, which is a geospatial extension of Pandas library, already introduced before. Please note, Geopandas supports some functionality that Pandas does, plus a wide range of spatial extension that make manipulation and general mapping of data, that's analysis of data, similar to non-spatial table. So in 2 lines of code, we will obtain a graphical representation of spatial data contained in a file that can be in many formats. Actually, since it uses the same drivers under the hood, you can load pretty much same kind of vector file from desktop GIS package like QGIS or S3. So let's start by plotting single layer in a crude but quick form. And we will build style and certification into it later on. So we can read any data. Is it shapefile? Is it which other data format do we normally use for Google Map, KML? Any format that we are used to, we can read it in Geopandas so that we can analyze it. So in this course, we'll be looking at all these things. Now, the city we read the other time, let's inspect it and see what is there. So let me run this. You see, this is the city. We have the city ID. We have the number of buildings in that city. Then we have a column for the geometry. That won't make a spatial. This column of the geometry will help us to plot it. So this allows us to quickly produce a plot by executing the following line. So we can quickly plot this city by just executing cities.plot, and it will plot immediately. Let's see. You see, this is the city and it's plotted. You see, it looks so archaic, not beautiful, but we will work on that as we move on. So if you call a single row of the column, you can also plot it. So like if I want to plot the first city in that table, I will just query it out by saying city.locate the first row, and the column you are going to plot for me is geometry, as we can see here. So, and as we do so, let's see. You see, that's the first city. If you like, you can query for another city. Let's query for city 2 and see how it looks. You see, so that's it. So it's so beautiful as that. Now we have lines. Similarly to the polygon case, if we pick the geometry column of a table with line, a single row will display the geometry as well. So for street, don't forget the variable street where we read in our street data. We can also plot it just like what we do for polygon right now. We can call the row and call the column and it will plot. Let's see. See, if it is for 0, don't forget the index starts from 0. Then let's say for 10, you can see it plots it. So that's the street. It's a line, and you see that this one is a close, maybe it's a closed street. Now, we can also plot the street, the whole of the street, in a single command by saying street.plot. And you can see this is the result. Again, this is not the prettiest way to display street, maybe, and you might want to change a few parameters such as color, the length, the etc. All of these is possible, as we will see below. So, but these give us a quick check of what line look like. So we just have a quick check of what we just imported or downloaded from internet. So we can also plot our POIs also. That's the bar, using the same approach. You see, these are the bars in Spanish. So let's style our plot now. What we plot, let's style it a bit. It is possible to track several aspects of a plot to customize it to particular needs. In this session, we will explore some of the basic elements that will allow us to obtain more compiled map. Note, some of these variations are very straightforward, while others are more intricate and require tinkering with the internal part of a plot. So they are not necessarily organized by increasing level of complexity. So number one thing we will consider in styling is changing the transparency. So we can change the transparency of all our POI by putting a parameter in the plot function and saying the parameter to be equals to 0.1. So this alpha parameter has a value that varies from 0 to 1. So it depends on how transparent you want your point to be. So let me run this and let's see the result. You see now we have a transparent point plotted for us. So what of if we want to remove all these axes? Yes, we can also do that. We can do that. And we will do that using this small code. Firstly, we create a subplot. We call a PLT. Don't forget, this PLT has been imported already at the top. Don't forget, this is the PLT that we are calling. So on this PLT, we call a function called subplot, and we tell it the number of subplots we want, just one. And this will return two values. It will return a figure and an axis. And we will store those return into F and AS. So the second part is we are going to plot the layer of the polygon on the axis. So we call that city, the city data, and say plot, and plot it on this axis. Then we want to remove the axis frame so that it will not show in our plotting. So we just call axis dot set axis off function. So we just call this, then we display what we have just plotted. So let's see how it works. You see, there's no axis in what we have plotted. So that's another way to manipulate. So what of adding title? We can add title to our plot just the same way. we set up the subplot, as you can see. Then we plot the street on the axis, which is part of the variable here. Then we add title. We just say figure dot subtitle, which is street in Zaragoza. So then we display it. Now let's see how that works. This one we have axis because we don't remove the axis, as you can see. So, and this is the title. So another thing, good thing we can do with this map is we can change the size of the map. We can change the size of the map. And we do that just the same way as we have been plotting using this first command. We create a subplot, which is 1. Then we give it a parameter called figure size. In this case, we want 12 by 12. Then we add layer of the polygon on the axis, just as this. Then we display what we just plotted. And let's see the result. As you can see, we have a bigger map now. So we can modify the border of our polygon. That's another cool thing we can do. Increase the line width, give it color, give it edge color, and so on and so forth. So in Geopandas, these are very, very easy to do. So now we create our subplots just as we have been doing. I give it a size of 15 by 15. Yeah, you can change it as you want it. Then add layer of polygon on the axis. Then set fill color, which is face color, and boundary color, which is edge color. That's what I want to do now. I just call city variable. Upon it, I call plot. Then I say line width should equals to 1. Face color should be red. Edge color should be black. And the axis should be axis. Just attaching this to this. Then let's run and see what we have. You see, we are now having beautiful map now. So that is what cool thing we can do about mapping. So another thing, we can do the same thing for street. That's line color. But in this place, we have line width. Line doesn't have fill, so there's no fill color for line. So let's know that. Then no edge color. So we just have color. The color of the line we want. You just specify. So, and you plot it. Let's see. So you see that our line now appear in red. So these are the cool styling we can give to our mapping or visualization. So let's know that. So now another thing we can do with spatial data, we can check the coordinate system, coordinate reference system. When we check it, we can transform it from one coordinate reference system to another. So the coordinate reference system is the way geographer and cartographer have to represent a 3-dimensional object. So we are all used to that. So one of the ways to check for the city that we just imported, we can just say .crs, and it will give us the coordinate system. In this case, the coordinate system is projected coordinate system of EGSG 25830, and you can see it's UTM zone 30. So that is, it gives us information about the coordinate system. So if you want to know more about this EPSG code, there's a link for it here. You can go to their website. You can check for the projection we have in Nigeria, like Menon, Datsun, Menon WGS. So that if you are transforming your data, you know the right code to use. So that's on that. So we can now reproject. And in this aspect of code, we'll be reprojecting using to CRS. Then we specify the EPSG code for it. So I want to reproject to WGS here. So I will say, and for WGS, the EGPS code is 4326. So this is the city. Then I call a function to CRS. In bracket, as I put the parameter for EGPS, which is 4326. Then I tell it to plot immediately for me. So, and set equal axis to be equal. That is the axis to be equal interval, equally or intervally placed. So let me run this. Yes, you see, the shape I have is a bit different because I have reproject. So that's how to do it. And you see the coordinate system has changed also. So it's now in WGS, that's lat long format. So now, another thing we can do with our map is composing multi-layer map. As you can remember, so far we have considered many aspects.
We have less than 10 minutes, so in case we are log out, we will just come back again. Is that okay?
No problem. So another thing we can do is composing multi-layer map. So far, we consider many aspects of plotting a single layer of data. However, in many cases, an effective map will require more than one layer. For example, we might want to display streets on top of the polygon of the neighborhood and add a few points for specific location. So, at the very heart of GIS is the possibility to combine spatial information from different sources by overlaying it on top of each other. And this is fully supported in Python using Geopandas. So for this session, let's select only the Zaragoza street table and convert it to lat long so it aligns with the street and POI layer. So let's do this. We want to select a city called Zaragoza in Spanish, and we call that, we query that out using the row number. Then we query all the information in that city, in that row. Then we convert it to WGS, and let's see what will be the result. So you see, this is the city, and this is the conversion value. You see now it's now in lat long. So I want to plot it, and I want to plot it up on top of its polygon. So now the same way, you set up a subplot, add the layer with polygon to the axis, and that one will be in yellow. Then add a layer with line on top of the axis, and that one will be in green. That's for the POI. So let's see what the results will be. You see, we are now combining two different layers together. Good. So another thing we can do is we can save our map. We can save our map to figures, and we can save it as PNG, JPEG, and so on and so forth. So to do that, it's still the same way. We have a code here specifying the subplot to be 1 and the figure size to be 12 by 12. Add a layer with polygon on top of the axis. So we want to plot this Zaragoza to be yellow. Then add the layer with line on top of the axis. Also want to plot the POI on top of that city. Then we want to save the figure as PNG. So let me call this figure Let me change this name to test 123.png. So let me run it, and please look at this side. The file will appear here. It will be saved on my system, my local system. So that's run, and as you can see, I have the file here, which I can open in another tab. Can you see? So you can save your map. Let me close this. So that's how to save your map. So what I used to save here is just this command, save figure. So please note that when we have the note, we can go through it ourselves. It's very explanatory. So that's that. Then another thing we can do, we can increase the resolution of our figure. Like here now, the DIP, the DPI, I can increase it, and I'll increase it to 500. So let me reduce the size to 12 by 12, not 15, so that it will not take too much weight. So I can replot the same thing I did up there, and we have the quality will be different. Can you see? The quality is different compared to this. So, and it's saved differently. So now that's that. And another thing we can do is we can manipulating spatial data table. The spatial table, let us not forget. Now another thing we can do is we can manipulate our spatial table, and once we have an understanding of how to visually display our spatial information content, let us see how it can be combined with operation learned in previous session about manipulating non-spatial tabular data. Essentially, the key is to realize that a geodata frame contains most of its spatial information in a single column named geometry, just as I've shown you before. But the rest of it look and behave exactly like non-spatial data frame. In fact, it is. Consider them all the flexibility and conveniency that we saw in manipulating, slicing, and transforming tabular data, with the bonus that spatial data is carried away in all those steps. So what we'll be doing here, one of the things we are going to concentrate on geodata frame, cut across many operations in traditional GIS operation. So one of it is area calculation, and we can easily calculate area from the geodata frame by just create a variable city area, and we call our city dot area, and that thing we just go and look for geometry in our city table and just calculate the area. So let's see what will be the results. You see the area that we have now. This indicates that the area of the first city in our table take up 8,450,000 square meter. If we wanted to convert it to square kilometer, we can just divide it by 1 million. So, and let's do that so that we can have a very small figure. As you can see, this is how to do such a small operation. Just like if you want to do more complex operation on your shapefile, you can bring in your shapefile, do the manipulation on this using this knowledge you are learning here. You can figure out scrutinize, clean up your data in the shapefile, then take it back to your ArcGIS or your QGIS software, and you will see the beauty of this course. So it makes you to do more operation that even ArcGIS and other GIS software may not give you at times. And you can write your own function to do your own calculation. So this package give room for that, and that's one of the advantage. So another thing we can also do is to get length, and we can get length based on particular projection. You know, the one we've used before is latitude and longitude. So, but we want to reproject this street data into UTM, that is meter base, then we get the length. So how are we going to do that? Just call the street, then transform it, supply the EPSG code, then just call dot length on top of it and run it, and we have the length. So this is the length. So expressed in meter. So that means the first street segment is just 37 meter length. Another thing we can do is getting the centroid calculation. That's the center of each polygon. So sometimes it is useful to summarize a polygon into a single point. And for that, a good candidate is its centroid. Almost like a spatial analog of the average, the following command will return geoseries. Don't let us forget in previous classes, I tell you the data structure we have in pandas. We have DataFrame and we have series. So, but here we are talking about DataFrame and geoseries. So please, let's relate it back to what we have learned, and it will be more clearer to us. So whatever you will get when you want to calculate a centroid is called geoseries, and you can plot it directly. So let's see how we can do it in a code. We have a centroid variable, you can give it any name you like, equals to city. We are calling our city variable dot centroid, and we want to print the first 5 rows out of it. So let's run it and see. So these are the centroid of all the polygon of all the boundary of the cities in Spanish. See how simple it is. Good. So now, since it's a geoseries, we can plot it straight away, and you can just call the variable name and say dot plot, and it will plot, as you can see. So we plot the centroid figure now. But you don't need to call a geometry column to inspect the spatial object. In fact, if you do so, it will return an error because geoseries already on its own is a geometry. Please, let's note that geoseries is on its own is a geometry. So you can perform any geometry operation on it directly without calling the property geometry. So another thing which I want us to note is that another thing we can do is to find a point, whether a point is inside the polygon. You can find whether a point is inside the polygon. So, like now, we define a variable called poly. We call our cities, and we locate the 112 row under the colon geometry, and we stored it inside this poly. Then we have some centroid that we have calculated. We call, and don't forget it's a series, so we can call them out by their index. This thing we have talked about it before. Series is the same thing as list, one of the data structure I talk about. But now we are giving it a good or a rebrand name. So I want to call the first centroid, which is centroid in curly brace or in bracket 0, the first one. Then I want to call the one that is in the row 112, and I'm attaching it to point 1 and point 2 respectively. So we cannot perform a check. The first check in this polygon, don't forget this polygon is polygon for row 112. That's city 112 by ID. So we want to know whether point 1 belongs to it. And before I even run it, we can guess what will it be, because this centroid 01 belongs to another one. It belongs to city 0. That's the first city. So I'm expecting to get a false that is not contained. Okay, I've not run this. Sorry. Let me run this. Yes, let me now rerun this. So I have a false. But if you look at point 2, which is actually the centroid of 112, so I'm expecting to get a true value that this point is actually contained in this polygon. Good. So performing points in polygon this way is intrusive and useful for pedagogical reasons. But for cases with many points and polygons, it may not be efficient. In this situation, it is much more advisable to perform them as a spatial joint. So if you use ArcGIS very well, that's what we call spatial joint. You will coil out what belongs to a particular polygon and put it in and create another new table or new shapefile for it. So we can join. It's a complex operation. So we can also do it with Geopandas. If you are interested in this, I put a link down this notes. You can visit it. There's a code there. You see how to do a spatial joint with Geopandas. Okay, let's continue. Another thing we can do is buffer. These are GIS terms, and buffer are one of the classical GIS operations in which an area is drawn around a particular geometry, given a specific radius. These are very useful, for instance, in combination with points in polygon operation to calculate accessibility and catchment area, etc. So for this example, we will use the bar table, but we project it to the same coordinate reference system as cities, so it is expressed in meter. So firstly, we will reproject our POIs, and we store that value in POI projected. So we are projecting our POI using this function to CRS, and we are using the coordinate information inside city CRS. So let's display what that information is after projecting. You see now we are having the same coordinate reference system for our POI now as it has been displayed here. So from there, we can create a buffer by just calling buffer. It's so simple. And they take only one value, which is the radius, 500. So we want to see bar. We want to see area that each bar can serve in that locality. So let's run this. So, and this is the result. So we can plot this just as we have discussed before to see the effect. Can you see? That's buffering. Now, adding, another thing we want to talk about is adding base layer. You have used Google Map before, and if you have used ArcGIS like ArcGIS Pro or QGIS with base map, we can do the same here, and very simple. So many single data sets lack contents when displayed on their own. So there's a need for a base map. A common approach is to alleviate these to use a web tag, which are a way of quickly obtaining geographic context to present spatial data. In Python, we can use a library called context tiling to pull down tile and display them along with our whole geographic data. So we can read more about this context tiling. This is their website where you can read more about it. You see, you can pull a lot of satellite imagery, straight maps. You can pull it out. So how to use it, how to install it in Python, this is it. So explanatory. You can go through it at your own leisure time. So we'll be using it here. And the way we are going to be using it, we use it by calling a function add base map. So we have an axis, we have city plot, and we give it color black. Then we want to add a base map to it. And we have to specify the coordinate system so that it will not give us an error. So let's see the result. It's pulling the tiles, it's running. So by the time it's done, it will give us our map. As you can see, it's still running. So note that we need to be explicit when adding base map. And as you can see, it has plotted this. You see the span now. You see all our map. You see the boundary also in black. So please, we need to be explicit by specify the coordinate reference system when using this function, unless we have an error. So another way of doing it, let me do it in another form here. It's running, as you can see. And what did I do? I have city. I reproject it to another coordinate system, and I plot it and add a base map to it. So it's as simple as that. So WebTile can be integrated with other features of map in a similar way as we have seen above. For example, we can change the size of the map and remove the axis. Let's use Zaragoza for this example. Don't forget we have a Zaragoza variable that's set GZS. So we create our figures just as before. I want to give it size 15 by 15 here. Then this Zaragoza, which is a point data, I will give it an alpha value, a transparent value of 0.25, and attach it to this axis. Then I will add a base map to it with this coordinate system attached. Then I will set the axis off. Let's see what will be the result. Still running. Let's wait for it. It has to pull those map files, plot it. Once it has pulled it from the internet, plot it. Beautiful. You see, you now have a very beautiful map with the base map attached to it at the background. You see the polygon with the alpha transparency. You see now it's showing how easy to style a map. I hope this is interesting. So we can do this, especially when we are presenting our results in a report format. You can have this, just go straight to your visualization. So, but this may not be good when we want a more interactivity with your map. We will still get down to that very soon. So now context styling offer a lot of options in terms of source and provider. You can use it to create your base map. For example, you can use satellite imagery instead. So let's use satellite imagery instead of the street map that I put at the background. So I'm running it already. Let's see what will be the results using satellite imagery. So, and you see that I specify some parameter here, source. My source is now cs.provider. When you read the documentation, you get all this in there. .s3, that means I'm pulling the S3 word imagery. And you can see this is the result. So have a look at this Twitter trend to see the different type of provider that we have. Let me run this Twitter trend. Oh, I think I might log into my Twitter, but if you like, you can visit this trend. Okay, it's done. You see, we have the satellite imagery. We have this type of terrain. That's what terrain. Then and so on. When we read this, we can get it. So now, what if we want to produce an interactive map? Everything we have seen so far are just a static map. These are useful for publication. You want to publish your research work in data science, your findings, those things that we have looked at is very good. But if you really want to engage your user, you have to make it more interactive. Now, to include in a report or to print, it's good to have a static one. However, modern web technology offers more flexibility to exploit spatial data interactively. One of the most prominent examples of interactive map integrated with notebook is called Kepler GL. We can read about this. Using its Jupyter integration, we can easily convert data expressed in lat long into interactive map and then play further to track the appearance. In this context, we will only show how you can take a geodata frame into an interactive map in 2 lines of code. No, this may not render on the website. So you call your Kepler and initialize its object as M. So it means you are creating a new map. Then you append your data to it. You just say M. Don't forget this M is coming from here. This is the variable. Add data. Just like clicking on add data in ArcGIS. And the name of the data you want to add, which is street. And the name you want to give it street. Give it a name. Then you can display it by just calling M. So let's run this, and that will be our final. So let's see. You see now, it's loading. So we have an interactive map. You see all the tools that you can use to switch to a dual view, 3D map, show legend. You see the legend. You can draw on the map. You can select a location on this map. You see, it's now using Mapbox as the base map. Beautiful. So now we are already at the end of this course, at the end of this lecture for today. So for further resources on how to use Geopandas, how to carry out spatial joints, you can visit this notebook, which I will be posting. Then to how to make a spatial overlay, you can visit this for further operation, GIS operation.